This first video was an introduction to standing waves. The first image that you have on your page there shows you a possible standing wave. With that wave, what you see are points on this wave where we have a region of maximum displacement and points where we have a region of no displacement. Okay, so this is the type of wave, all right, that you're going to see when we created in class with the spring, where we had two people at each end holding it, all right, and creating a wave that looked like it was staying in place. All right. So to begin this conversation, let's talk about the different points that are in phase and the different points that are out of phase. All right. The points that are in phase here, all right, I'm going to circle all with the same color. We're going to have A, E, and I. Points that are in phase as well are B and F. Keep going here. C and G are both in phase. And D and H are both in phase. All right. So the idea, any two points that are in phase, okay, the phase difference between them is 0. So in phase difference, we'll call it this, is equal to 0. What that means, the phase difference, okay, is how much they're separated by in radians, okay, through how much they've gone through in the cycle. So the cycle starts at 0 and goes through 2 pi radians as it moves through the entire cycle. In other words, where it is along the unit circle is where you can think of it. All right. For the points that are completely out of phase, though, all right. So I'll just clone this page here. There we go. And the points that are completely out of phase, in this case, are going to be A and C, and B and D. And let's see here, what else? We could also say F and H. All right. We could also say, actually, that we'll go with A and G here as well. Okay. And what we're showing here, the phase difference here, the point at which these points are in the cycle, this phase difference is some multiple, okay, of pi or 180 degrees. Right? In other words, they're on opposite sides of the unit circle. So before, when they were in phase, they're at the same point in the unit circle, okay, moving together. Out of phase, they are on opposite ends of the unit circle, moving in opposite directions, okay, through that phase. So that's just to get you started thinking about what phase is, okay. It's the phase of any particle is its position in its cycle of oscillation. We're going to be combining this, all right, we're going to be talking about phase a little bit when we start talking about interference here, all right. So the first thing to think about, all right, is reflection of a pulse, okay, at a boundary. I showed this to you in the wave demonstrator. I'll show it to you again on Friday. But if you were to send the pulse down a rope, okay, and that rope had a free end, what would happen is that this pulse would travel down, and the rope would go up, all right, and back down as the pulse energy, all right, was reflected back the other way. But if you have a fixed end, like you have right here, okay, and so this fixed end, this is how we draw a fixed end here in engineering, okay. In other words, what's going to happen is it's not going to move. And that pulse hits the end here, all right? Newton's third law, what's going to end up happening is that the rope is going to push up on the wall, and the wall is going to push back down on the rope. When the rope pushes back down, when the wall pushes back down on the rope, all right, what it's going to do is push that pulse to the other side and send back a reflected pulse, all right, that is inverted, is upside down, excuse me, okay? So that's basically what's happening here, and I've showed you guys that before. So if we combine, okay, reflection with another idea, which is the principle of superposition, we're going to get our next idea. But first here, the principle of linear superposition, when two or more waves meet, the displacement of the resultant wave is just the vector sum of the displacements of the component waves. So the first example we have there is an example where we have constructive interference. Here we have two waves meeting, they're heading towards each other, and when they overlap, okay, the superposition of these waves, all right, basically both of these pulses are in phase together, and their amplitudes are going to add up to something greater, as you can see right here in this example, right? And also in this example, we have two pulses of different heights, and they add, okay, each point is being added together, okay, of each wave. So we come over here, and let's just say, like right here and right here, both those add up to right there, okay? Same thing, these two right here add up to right there, these two here add up to right there. So you're basically looking at, lines straight down as the addition of their amplitudes, okay? Right here, again, you see right here and right here adds up to right there, okay? And once both pulses travel through each other, they keep going on their in their respective directions. Okay, so destructive interference, this is where we have both, when you have both waves, the superposition of both waves, okay, when they're out of phase with each other, they end up canceling each other out, right? So when we see this here, there's nothing happening there, okay, when we see both those waves. We'll do some demonstrations in class. Again, here, same type of a thing. We add this and we add this, what we end up with is something in the middle, okay? So what we see is a canceling out, a smaller amplitude than the largest amplitude of either of them on their own is what you end up with, okay? So moving on here, okay? Again, two more examples of constructive and destructive interference here. And we'll play around with this a bit more in class on Friday. Now, let's put both these ideas together, okay? You had reflection at a fixed end, okay, combined with superposition, and what we end up with, okay, is a standing wave. If we have one end of a string vibrating, okay, sending a pulse down the wave, it's going to be reflected at the other end, right? That end could be free or it could be fixed, actually, all right, either way, but eventually that pulse is reflected, and if that pulse is reflected and if the pulse is at the same frequency at which it's being reflected back, in other words, they both interfere consistently, all right, in the same phase, what we end up with is a standing wave. Okay, so a standing wave, again, we'll make a note of this, is a result of two things that happen here. Result of reflection and superposition. These are the two phenomena that a standing wave result from. And when we end up with this, you see this is something familiar from what we saw in class, okay? Now the locations, there's different characteristics here of this type of a wave. What we have is a node and antinode, all right? These two little vocabulary words that you guys need to know, all right? And the node is a place where we have complete destructive interference, there's no displacement. Antinode, all right, is a location of maximum constructive interference, all right, where we have the maximum amplitude. And so we have here, all right, pretty much that's the anatomy of a standing wave, really, all right? We don't refer to it as a trough or crest or anything, just antinodes and nodes. So there's a difference between standing waves and traveling waves. The traveling waves are the ones that continue traveling through a medium, okay? For a standing wave, energy is not transferred, doesn't end up going through it, it's just stored in it, okay? So energy, just stays within that string. Okay, that string vibrates and it just holds onto it, doesn't transfer it anywhere, all right? Amplitude along a standing wave is variable. For a traveling wave, we say it's fixed, okay? All right, and that it continues along through the medium. The wavelength is the same with the component waves, okay? It's equal to twice the distance between any two consecutive nodes or antinodes, all right? So what they're saying is that twice the distance between any two consecutive antinodes, so between here and here, twice that distance obviously is one wavelength. All right. The frequency, again, all the particles oscillate in simple harmonic motion up and down in a standing wave, and with the same frequency as the component wave. And when we're talking about the component wave, they're talking about the traveling wave that you're sending using this oscillator right here. Okay. Again, the phase and phase difference. All points in one section between two consecutive nodes or antinodes are moving in phase. In other words, all these points are in phase in between here, okay? Over here, all these points are in phase, but the two sections next to each other are completely out of phase, okay? The two sections, that is. All points within one wavelength have a different phase for a traveling wave. Okay, so every single point is in a phase difference within a traveling wave. So we'll play with this some more. We'll do some simulations on it on Friday and show you some examples of the demonstrations with the wave demonstrator. But that's just an introduction to standing waves.